Today, we're going to go looking for beauty. But we're not heading to an art museum or anything like that. Nope, we're going to find it inside a math problem. And you got to stick with me here because the mystery we're about to dive into is seriously cool.
So what even makes a math problem beautiful anyway? Is it when you get a nice, clean answer, or is it something else? That's the big question we're going to tackle today.
All right, so for the next couple of minutes, let's all put on our mathematician hats. And don't worry, you don't need a calculator for this, just a little bit of curiosity. Think of it like a detective case, where the clues are all numbers. Now, every good detective story starts by establishing the facts, right? So let's begin with a really simple, super reliable pattern, one that works perfectly every single time. You've probably seen this one before. And here it is, the famous Pythagorean theorem. Look, if you take 3 squared and you add 4 squared, you get 9 plus 16, which is 25. And what do you know? 25 is exactly 5 squared. It's clean, it's perfect, it just works. And this is no fluke. Let's try it again. How about with 5 and 12? Well, 5 squared plus 12 squared, that's 25 plus 144, which gives us 169. And would you look at that? That's a perfect 13 squared. See? The pattern holds. Okay, one more, just to be absolutely sure. 8 squared plus 15 squared gives us 289, which is exactly 17 squared. So, we've got ourselves a solid, predictable rule here. This is a pattern we can count on. And here's the most incredible part. There are endless combinations of whole numbers that solve this equation. Infinitely many. It is a beautifully consistent rule baked into the universe of numbers. All right, now for the plot twist. What happens if what if we mess with this perfect pattern? Let's take that beautiful, reliable equation and just make one tiny little change. So instead of squaring the numbers, multiplying them by themselves twice, let's cube them. We're just going to change that little 2 into a 3. So the new question is, can we find any whole numbers for x, y, and z where x cubed plus y cubed equals z cubed? Does our perfect pattern still work? This, my friends, is where our detective story really kicks into high gear. Mathematicians have spent centuries hunting for a solution to this. You can try it yourself. Just pick any 2 numbers, cube them, add them up, and see if you land on a perfect cube. Let's try one right now. How about 6 and 8? Okay, 6 cubed is 216, 8 cubed is 512. We add them together, and we get 728. So, is 728 the perfect cube of some whole number? The answer is no. But get this, look how agonizingly close it is. The very next number, 729, is a perfect cube. It's 9 cubed. We missed it by 1. How frustrating is that? And you can keep trying. You can fire up a supercomputer and test billions of combinations, huge numbers, tiny numbers. You'll find more and more of these near misses, but you will never, ever hit the bullseye. Because here's the truth. It has been proven that there are 0 whole numbers in the entire universe that solve this equation. Not one, never. The pattern isn't just a little off, it's completely, totally broken. So there's our answer, right? It doesn't work. Case closed. But for a mathematician, that is not the end of the story. That's the beginning. See, the really interesting part isn't what the answer is, it's why. Why? Why does this pattern that has infinite solutions for squares suddenly have 0 solutions for cubes? Let's really break that down. Why is there this bottomless ocean of answers for squares, but a total desert for cubes? What on earth is so different between the number 2 and the number 3 that causes this massive, dramatic change? And this right here is where we find the real beauty. It's not in the predictable, working pattern. It's in the deep, profound mystery of the broken one. The beauty is in the quest for why. This really just says it all, doesn't it? The point isn't just to notice that a pattern breaks. It's to figure out the deep structural reasons for it. And the proof for this problem, for example, it connects totally different areas of math in ways no one ever imagined, and it reveals these incredible new truths about the nature of numbers themselves. So the big takeaway here is that the beauty wasn't in the easy, repeatable pattern of the squares. The real treasure was hidden inside the stubborn, impossible problem of the cubes.
The journey into that mystery is what really pushes our understanding forward.
And that just leaves us with one final thought to chew on. What other simple, obvious patterns that we all just take for granted might be waiting for one tiny little change to unlock a deep and beautiful mystery? Thanks for joining me.